So far we have seen that whenever a user opens a program, a process will be created. Okay, which means when in case if a user opens a program three times, three processes will be created for the same program, right? Now this program for which the process is created is also called as passive entity. Okay, it is also called as passive entity. Whereas, yeah, the process which is actually created for the program is also called as active entity. The name itself suggests, right? The process is actually active, which means it is being executed by the CPU. Whereas our program is not doing anything, right? It is simply creating once the process is created, then actually we are not using the program. Like actually we are using the program for further creating processes, but apart from that, we are not using the program anything for anything else, right? Only we are using the process, which means we are moving the process to RAM, and then the process is being executed by the CPU and all, right? So this is one point I wanted to discuss. Okay, a process is also called as active entity, whereas a program is also called as passive entity. Fine. Now, not now for we know that for every program a process will be created whenever user opens the program. Now the process will not only contain program, it will also have some more thing, right? See, this is a process which is created for a particular program. Okay, as we know, the process will definitely contain the program. Now, apart from program, it will also have some more things. See, our program will be full of functions, right? Our program will have a lot of functions. For example, our program will have a lot of functions. And now within a particular function, there are chances of having function calls, which means within the function f1 I can have a function call, say f2, which means I'm calling function f2 from function f1. From function f1 I'm calling f2, right? Now in order to this can keep on happening, which means nested functions can happen. For example, f1 might call f2, f2 might call f3, f3 might call f4, and this might keep on going, right? Now just to keep track of the function calls, we need something called as stack. Okay, that is the reason we are having this stack memory. See, we are going to have a stack is nothing but just a memory. Okay, now whenever f1 is called, f1 will be pushed into the stack. Now whenever f1 calls f2, f2 will be pushed into the stack. Whenever f2 calls f3, f3 will be pushed into the stack, and this will keep on happening. Now once this is done, the order of execution is nothing but f3 followed by f2 followed by f1, which means f3 will be executed. Once it is done, f3 will be popped from the stack, then f2 will be executed. Once f2 is done, it will be popped from the stack. Once f1 is done, this will be popped from the stack. Then that's it, the program has completed its execution, right? This is what we will be doing. Now for this we use something called a stack. See, every program will have lot of functions, and within the function there is a high chance of function calls. Now just to keep track of the function calls, we use something called a stack. Okay, fine. Now our program might also have something called as dynamic memory allocation. Dynamic memory allocation is nothing but allocating memory using malloc calloc. Okay, for example, in C programming we use two function calls, right? Malloc and calloc. These function calls are actually used to dynamically allocate memory. What is meant by dynamically allocating memory? Allocating the memory at the runtime. Okay, that's what we mean by malloc calloc. Now whenever we use this malloc or calloc within our program, which means this program, this heap space is actually used for those dynamic memory allocation. For example, in case if some space is allocated using dynamic memory allocation, now this space will be allocated within this space heap, right? Now there is no fixed space for stack or heap, which means some programs may need more space for stack, which means it might have a lot of function calls, whereas some functions may need more space for heap, which means those programs will have more dynamic memory allocation, right? So they are actually dynamic, which means the heap will be growing upwards whereas the stack will be growing downwards. Some programs may need more space for stack. In that case, stack will go till here, whereas heap will be having only this space. In some programs, heap may need more space. In that case, the heap will be allocated more space, something like this, whereas stack will be having very less space. Okay. In simple words, what I want to tell is this space is not equally divided between stack and heap. It really depends on the program. Some programs may need more space for stack, whereas some programs more space for stack, whereas some programs may need more space for heap. So the amount of space which is allocated to stack or heap among this total space really depends on the program itself. Okay, it varies from one program to another. Fine. Now this complete process which is created for a program is also called as process control block. Okay, it is also called as process control block, PCB. Now for every process we will be having a process control block. In case if we have 10 processes, then we will be having 10 process control blocks. So in here our RAM, this is our CPU and this is our RAM, and as of now there are 3 processes named P1, P2 and P3 along with the OS code in the RAM. Okay. Now this P1, P2 and P3 is nothing but the PCB, which means this is PCB of P1, this is the PCB of P2 and this is the PCB of P3. Okay, fine. So far we have seen that a process will not only contain just program, but it will also have some more things like stack, heap and static and global variables. See, what is meant by static and global variables? Within our program, we might use static keyword, right? For example, in case if I wanted to declare a variable as static int I, okay, these variables will be separately placed in the static variables. See, in case if it is a local variable, what is meant by local variable? A variable which is defined within a function is called as local variable, right? Now for local variables, the space will be allocated within the stack, which means we have already seen that all function calls will be stored within the stack. Now in this activation record for F1, what are all the variables which are created for F1 will be placed, okay, all the local variables. Similarly for F2 there can be lot of local variables. All the local variables of F2 will be placed over here. This is how local variables are allocated. But the variables like static variables or global variables will be allocated separately. Okay, they will not be allocated within the stack. They will be allocated within. They will be actually allocated in a particular space inside the PCB. Okay, this is what we mean by process control block. Fine. Now, in case if you didn't understand the static and global variables, you might have to go through the basics of C programming. Okay, in case if you go through the basics of C programming, you will be able to get this. Fine. Now let's see what are the various attributes we have for a process. Okay, attributes is nothing but properties. See, for example, if I am a person, I may have a lot of properties like my hair is curly, my skin tone is brown, I am wearing glasses. Like that, I have a lot of properties for me. In a similar way, for every process there will be some attributes. Okay, every process, first thing is nothing but process ID. Okay, process ID is nothing but a unique number. Every process will be assigned a number and that number will be given to only this process and not to any other process. Okay, that's what we mean by unique, which means every process will be having a unique number, and that number we also say that as process ID. Okay, fine. Now there is something called as program counter. Okay, program counter. See, what might actually happen is, let us assume this. Let us see this first. Let us assume we have a CPU, okay, and P1, P2 and P3 are the 3 PCBs of 3 processes which are placed inside the RAM. Now, within P1, P2 and P3, one of them will be executed by the CPU, right? Let us assume all 3 of them, P1, P2 and P3 wanted CPU, okay, they are in ready state, which means they are ready to be picked by the CPU for execution, okay. Now, in that case, CPU might have to select one, not CPU, operating systems might have to select one among the 3 processes to be executed by the CPU. That is what we have seen. That is the main functionality of OS, right? OS functionality is nothing but resource allocation, which means the resource here is CPU. Now the CPU has to be given to one of them, one of the three processes. Now how is that being done? That is being done by something called as our operating system's code. Now the part of the code, see, OS code is nothing but actually a very big program. You already know that, right? OS code is a big program. Within that part there will be some part of the program which will be actually used in order to define which among the three processors should be selected by the CPU. That part of the code is also called as scheduler. Okay, scheduler is nothing but a program which is part of our OS program. This is our OS program and this is the program which is scheduler, and this scheduler will have the code to say that in case if more than one process needs the CPU, which among them should be executing the CPU first. That is very important, okay? Which is executing the CPU first. See, every process will of course get the CPU. There is no doubt about that. But what is the order in which they will be getting the CPU? That really matters, right? And that is being decided by our scheduling algorithm, which means this is nothing but the scheduling algorithm. Okay, this is the code. Now, this code can be implemented in lot of ways, right? This code can be implemented in lot of ways. For example, among all these processes, whichever process which came to the RAM first should be executed by the CPU first. That is one algorithm. We also say that as first come first served scheduling algorithm. What is meant by scheduling algorithm? The algorithm which is used to actually select one among these many processes to be executed by the CPU. That is what we mean by scheduling algorithm, right? There are various scheduling algorithms, and one such scheduling algorithm is first come first served scheduling algorithm. Now what this scheduling algorithm will do is, among all the processes which are present inside the RAM, it will choose the process which came first to the RAM. Okay, the process which came first to the RAM, which means let us assume P1 came to the RAM first before P2 and P3. Then P1 will be given the CPU first. That's what first come first served scheduling algorithm will do. In a similar way, we have lot of scheduling algorithms. For example, there is another scheduling algorithm named as shortest job first scheduling algorithm, which means among the three processes, let us assume P1 needs 5 nanoseconds of CPU, okay, to complete its execution. See, these problems we will be seeing it in a more detailed way. Now we are just having a rough overview, okay. Let us assume P2 needs 3 nanoseconds to complete its execution and P3 needs 2 nanoseconds to complete its execution. Now among these three, the process with the shortest execution time will be executed first. That's what shortest job for scheduling algorithm says. Okay, shortest job for scheduling algorithm says whichever process is having the shortest whichever process which is requiring a shortest execution time should be executed first. Okay, now among these three, P3 needs the shortest execution time, right? It needs only 2 nanoseconds from the CPU, whereas P2 needs 3 nanoseconds from the CPU, P1 needs 5 nanoseconds from the CPU. So P3 will be selected by the scheduler to be executed by CPU first. Okay, so this is just a rough overview. Okay, we will be seeing this scheduling algorithms in more detail with a lot of problems. Fine. Now why I have explained these things is just to explain you that what is meant by program counter. Okay, now what might happen is, let us assume some process is being scheduled to the scheduler. By the scheduler, let us assume some process is being scheduled by the scheduler to the CPU. Okay, let us assume CPU is actually executing process P1. Okay, now what might happen is, there might come some other process. Let us assume process P4. Let us assume we are using shortest job first scheduling algorithm, which means the process with the shortest execution time will be executed first. Okay, here P3 has the shortest execution time, so the scheduler has scheduled process P3 to the CPU. Okay, which means CPU is actually now executing process P3. Now let us assume a new process P4 comes into the RAM. Okay, now this needs, let us assume, just 0.5 nanoseconds from the CPU. Now what we should be doing is, this is actually a lesser time than this, right? This needs lesser amount of CPU, whereas this, let us assume P3 needs more amount of CPU. Okay, now in that case, this process P3 has to be forcefully stopped, which means this process has to be stopped from execution of CPU, okay, and some other process P4 has to be scheduled by the scheduler. Okay, see, P3 is not yet completed. Okay, P3 is not yet completed, but it is stopped for some temporary amount of time until P4 is getting completed. Now once P4 is done, we will be executing P3. Okay, so what we are doing here is, whenever we are executing a particular process, in case if a higher priority process comes, here priority is being calculated based on shortest job, right? Whichever is the shortest job, that will be given the higher priority. That will be executed first. Now here, since once a high priority process comes into the RAM, the low priority process is being preempted, and we take the high priority process and then we execute it. Okay, so what is actually happening is, so once P4 is done, we might have to continue with P3, right? See, once P4 is done, P3 is not yet completed. Only some part of P3 is completed, and then we move to P4. Now once P4 is done, we might have to continue from the place where we left off P3. See, P3 is a program. It will have lot of lines. Let us assume while executing this part, we actually preempted P3 and we scheduled P4. Now once P4 is done, we might have to continue P3 from the place where we left out. Okay, so how is it possible? How will we remember the place where we actually left out? Now for all these things, we use something called these properties. Okay, program counter will actually say the instruction number. Instruction number is nothing but line of program from where I need to continue the execution. For example, this is first line in the program, this is second line in the program, this is third line in the program, this is fourth line, this is fifth line. Let us assume we have executed P3 till third line, and then we scheduled P4, okay, because P4 is having higher priority than P3. Now let us assume P4 is done, execution of P4 is done by the CPU completely. Now we will be again moving to P3. We need to start execution from line number 4. Now how will we know that we should start execution from line number 4? That is being indicated by something called as program counter. Okay, program counter is nothing but a register which will be maintained closer to the CPU. Okay, this is also called as program counter. This register will hold the number. So far we have seen that when process P3 is being executed by the CPU, let us assume process P4, which is of higher priority, came to the RAM. Okay, now we might have to preempt P3, which means we might have to forcefully stop CPU from executing P3, and then the scheduler will schedule process P4. Now P4 is being executed by the CPU. Okay, let us until line 3 of process P3 is done and P4 is being scheduled. Okay, now once P4 is done, we might have to proceed from line number 4 of P3. Now this line number 4 is being remembered by something called as program counter. Now similarly, general purpose registers actually remembers which are the register values which are used by process P3. Okay, see, process P3 will have, while executed, when it is being executed by the CPU, should have used some registers. For example, this register is having a value of 5, this register is having a value of 6, this register is having the value of 3, this is having a value of 2. Okay, until the execution of line 3, these are the values which are being stored in the register. Now these values has to be used, will be used by P3 while executing line number 4 and 5. So these values have to be somehow remembered. Okay, when we continue with P3 after completing P4, right? Now for that purpose, we actually store all the register values. Okay, that is what we mean by general purpose register. For every process, we will be having a set of register values, and these register values has to be remembered whenever we are preempting that process from execution by the CPU. Why? Due to scheduling algorithms. Okay, fine. Similarly, there will be a list of open files, which means the files which are opened by process P3. That has to be also remembered. Okay, see, files are So there will be some files for, we've seen that what is meant by an IO, right? IO is nothing but reading something from some IO device, especially reading some files from the IO devices. Now this process P3 should have actually opened some files. Open means it should have started reading some files. Let us assume it has read half of the file after executing line number 3, until executing line number 3. Okay, now the reading of that file from the left out part has to be continued. Okay, for that reason we remember the list of open files which are being done by our done for the process P3. Okay, we will be remembering it. Similarly, we have list of open devices. For example, process P3 should have used the printer for printing a page. Okay, now until let us assume for printing a complete page, we have printed half of the page. Okay, now process P3 is being preempted. Being preempted means being stopped forcefully from execution by CPU, and P4 is done. And once P4 is done, P3's printing has to be continued from the place where we left out. Okay, so we use something called as list of open devices, which means the devices which are being opened by process P3 should have been remembered when we continue after being preempted. Okay, so we use this. Now what is meant by protection is, when a particular process has some space, right? It has something called as stack space and heap space, which means for function calls it uses the stack space, and for dynamic allocation, for dynamic allocation of space, it uses the heap space. Now the process P3 will have a particular stack space and heap space, and process P4 will also be having its own stack space and heap space in its PCB, right? Now P4 should not access this space, as well as this process should not access this space. Okay, that is what we mean by protection. And for every process, our operating system needs to make sure that it is not using the space of a process is not using the space of another process. Okay, that is what we mean by attributes. I know it is a bit difficult to understand it very clearly the first go, but as we keep progressing, you will be able to understand most of the things. Okay, fine. Now these are the various attributes of a particular process. Now let's see a very interesting topic named as scheduling algorithms, CPU scheduling algorithms. Okay, fine.